This is Unit 12, Stoichiometry, Part 2 notes. So by the end of this unit, you should be able to perform stoichiometric calculations to determine the limiting versus the excess reagents. Those are your reactants. And then you should also be able to calculate the percent yield of the reaction. Okay, so just to review a little bit, stoichiometry, these are mathematical conversions between the amounts of substances in a balanced chemical reaction to determine the mass of each substance based on either product production or reagent consumption. So we did this the first lecture. That was our mole to mole, mole to mass, and the mass to mass conversion, so your 1 step, 2 step, 3 step. But then today we're going to talk about which reagent limits the amount of product that can be produced, or the percent yield in the reaction. And it's all, again, based on this mole to mole ratio, where we look at the coefficients of a balanced chemical reaction. So those coefficients are going to be important here. So as always, make sure you're able to balance that chemical reaction first, and then we'll be able to do our calculations. So there's two types of reagents. The first one is called a limiting reagent because it's the reactant that's going to determine the amount of product produced, and it's going to produce the least amount of your product. And then we have the excess reagent. That is the reactant that is not completely used up in a reaction, and you'll have some left over. For example, if you look at the reaction down here, we're going to combine carbon plus molecular oxygen to produce CO2. Well, in a carbon dioxide molecule, you always have to have one carbon. So your 5 carbon atoms could potentially only produce 5 carbon dioxides because each one needs a carbon. But then you have 10 oxygen molecules. Potentially, each one can produce a carbon dioxide molecule because you have to have 2 oxygens. So potentially this reactant could produce 10 carbon dioxides, but what limits us in this reaction is the carbon because there's only 5 and you have to have carbon to make carbon dioxide. So your carbon would be the limiting reagent while your oxygen would be the excess reagent because you have lots of this left over. Relating limiting and excess reagents to something as in making sandwiches, we can look at the combination of 2 slices of bread, 3 pieces of lunch meat, and 1 slice of cheese. So each of these reactants are needed to make 1 complete sandwich. But if we have as reactants 6 slices of bread, 12 pieces of lunch meat, and 5 slices of cheese, how many total sandwiches could we make? Well, if we need only 2 slices of bread, then maximum 3 sandwiches can be made based on our bread. If we have 12 pieces of lunch meat, we could potentially make 4 slices of bread. 4 sandwiches. And then if we have 5 slices of cheese, we could potentially make 5 sandwiches because only 1 is needed for us to make a complete sandwich. Well, as we said before, the limiting reactant produces the least amount of our product. So the limiting reagent in this type of problem would be our bread because only 3 can potentially be made. But then our excess reagents, lunch meat, and cheese will be left over because they can produce more, but what limits us here is going to be our pieces or slices of bread. So in our limiting reagent practice example, we have to first balance this equation. And what we have to look for here is the oxygen count because a 3 and a 4, the lowest number that they can get to would be a 12. So I'm going to put my coefficient of 4 in the front here, so we'll have 12 oxygens. And then I'm going to put a coefficient of 3 here to also get 12 oxygens. So then I look at my aluminums. 4 times 2 is 8. We'll need 8 on the right side. And then we have 3 times 3 is 9 irons on the right, so we'll have to put a 9 here. So we have 4, 9, 3, 8 as our coefficients in this chemical reaction. And the problem is saying in A, if 25.4 grams of aluminum oxide is reacted with 10.2 grams of iron, determine the limiting reagent. Well, just like we did before in our sandwiches, we looked at all 3 types of reactants. So we're going to have to look at both types of reactants here. And what we're going to do is we have to convert to the same product. Doesn't matter which one you choose if they don't tell you which one to go to, but I'm going to kill 2 birds with 1 stone, and I'm going to convert to grams of Fe3O4 because I'm eventually going to have to do that later. So I have to write both of my givens down. So we have 25.4 grams of Al2O3, and then I also have 10.2 grams of Fe. I'm going to do a gram to gram ratio, so it's 3 brackets for both of them. Okay, so then grams of Al2O3 come straight down. I'm going to convert to 1 mole of it, that's molar mass. And if you calculate the molar mass of 2 aluminums and 3 oxygens, you should get about 102. Then you do your mole of aluminum oxide to moles of Fe3O4. You get those coefficients from the balanced chemical reaction, which should be 4 on bottom and 3 on top. And then we'll go back and do our mole to gram conversion, where now the molar mass of your Fe3O4 is 232. So when you multiply everything across, you get about 17,678.4 all over 102 times 4, which is 408. So then dividing those numbers and rounding to sig figs, you get 43.3 grams of Fe3O4. Then in the second conversion, again we're doing a gram to 1 mole conversion, but now we just look at the molar mass of iron, and then we do our mole of iron to mole of Fe3O4. Those are the coefficients. So now we have a 9 on the bottom and a 3 on the top. And then we do our mole to gram conversion, that's using molar mass, and again we'll get 232. So if you notice, the last 3 brackets that we filled in should be the exact same because you have to convert to the same unit of the same product. So whenever you multiply everything across on the top, we get 7,099.2 all over 504. So then dividing 70,099.2 by 504, we'll get 14.1 grams of Fe3O4. So then you look at the least amount of product produced, that was 14.1 grams, so that's going to make your iron, your limiting reagent. So your limiting reagent is going to be iron because it produces the least amount of your product. So hopefully, oh, I can't erase any of that. So we're going to keep, let me go right back for 14.1. Okay, so then B, we have to determine the number of moles of aluminum produced, and so we have to use the given that we have, 10.2 grams of Fe. That's going to be a 2-step bracket because we need to go to moles. So then grams of Fe comes down, that's molar mass, and then we'll do a mole-to-mole ratio. So moles of Fe is on the bottom, moles of aluminum is on top. So then those numbers come from the coefficients. In front of iron, we have 9. In front of aluminum, we have 8. So multiplying everything across, we will get 81.6 grams over 504. Dividing those two, you should get 0.162 moles of aluminum. So again, that's based on your limiting reactant. So the first thing that we have to do is you have to determine what the limiting reactant is before you can do any of those other calculations. So that was for B. And then C, we have to determine number of grams of Fe3O4 produced. Again, that's based on our limiting reagent, which is iron, and you've already done that calculation. So it's 14.1 grams of Fe3O4. So there's C. So you did A and C pretty much all in the same type of problem, and just kind of put an arrow going back to the work that you've just done. And then the last question, we have to determine the grams of excess reagent left over in the reaction. Well, if only 14.1 grams of Fe3O4 was produced, we have to do a gram conversion back to our excess reagent, which is our aluminum oxide, to determine how much was actually used. So then we do a gram to mole conversion, and the molar mass of Fe3O4, we've already done this, which is 232. Then we'll do a mole, Fe3O4, to moles of aluminum oxide. So then those coefficients are a 3 on the bottom and a 4 on the top. And then we'll do a 1 mole to gram ratio, which is 102 at the top. So you multiply everything across, and we get 5,752.8 over 696, if you divide the top number by the bottom number, you'll get 8.27 grams of how much that reactant was actually used. And then to find out how much was left over, we have to take that original amount that we had, which was, what, 25.4? So then you'll take 25.4, subtract it from how much was actually used in the reaction, and then you should have 7.1 grams of your aluminum oxide left over. Sorry, this is so messy. I don't have that much room, so hopefully you understood that. If not, just kind of write it down in sequential order, and then if we have to clear up some of the calculations or math, we will do so in class. So percent yield describes how efficiently a reaction proceeds, and it's based on this equation where percent yield is equal to the actual yield divided by theoretical yield, and we're going to multiply that by 100%. The actual yield is the actual amount produced in a reaction. So this is what you actually do in a lab, and that's going to be based on your laboratory technique. And then your theoretical yield is going to be the amount of product that should theoretically formed according to stoichiometric calculations. So your actual yield is going to be based on actually doing the lab, and then your theoretical yield is going to be based on those stoichiometric calculations. So if a question asks you to determine the percent yield, if the theoretical yield was 11.3 grams, but only 5 grams of water was actually formed, we'll just plug it into the formula, where you have actual divided by theoretical. So your 5 was what you actually formed, and then divide that by 11.3, which was your theoretical, multiply that by 100%, and you'll get 44.2%. And then just to clarify, if the theoretical yield is not given, then you have to calculate it based on stoichiometric conversions. So you'll have a given, and then you'll have to do some sort of stoichiometric calculation, most likely a gram to gram, since everything is in the gram. So just kind of be aware of that. Alright, so have you accomplished the objectives? If you are unclear with any of the calculations, please make a note in your ISN of what you did not understand, and I'll be sure to clarify any of the calculations, especially on slide number 9, the next time we have this lecture.